This is a video from section 4.9. A function capital F is called an antiderivative of little f on an interval I if capital F prime of x is equal to little f of x for all x inside the interval I. Now we have a theorem. If capital F is an antiderivative, as I erase that, which I didn't want to do, antiderivative of little f on an interval I, then the most general antiderivative of f on I is capital F of x plus c, where c is an arbitrary constant. And with that in mind, we're going to look at some directions. Find the most general antiderivative of the given function. Check your answer by differentiation. Okay, so we're going to go over some examples here. So suppose I had f of x equals 6. Well, if I want capital F of x, I need to think of a function whose derivative is 6. But remember, I know that the derivative of x is 1. So the derivative of 6x is 6 times 1, which is 6. So the answer here will be 6x plus some constant c. And again, if I want to check this, if I take the derivative of 6x plus c, that should be a c, I get 6 times 1 plus 0, which is 6. So it checks out. You get exactly what you started with, and that's what you want. Example 2. Suppose I had f of x equals 2x. So I want a function so that when I take the derivative, I get 2x, and you're going to find that that's x squared. And remember, if we want to check, and we need a c because we want the most general antiderivative. If I take the derivative of x squared plus c, remember that c is constant, and so we should get 2x. And that's what you want. That's the original function. Example 3. Suppose I had g of t is 3t squared. So if I want capital G of t, think of a function whose derivative is 3t squared. And you're going to find that that's t to the third, because I have to add 1 to that exponent. And then I just add c, because the derivative of any constant is 0. And so if I want the derivative of t to the third plus c, that's the same as 3t squared plus 0, which is equal to 3t squared. And that's what I want. That's exactly what we started with. Example 4. Suppose I had f of x is secant squared x. So now, again, you want to think backwards. Think of a function whose derivative is secant squared x. So in other words, you want to be thinking this. d dx of what is secant squared x? And I claim the answer here will be tangent x plus some constant c. And of course, if we insert that into the brackets, it checks out nicely because the derivative of a constant is 0, and the derivative of tangent x is secant squared x. Example 5. Suppose I give you this one. F of x is 2x to the 4th power. Something like this. Now, I need the antiderivative of 2x to the fourth. So I need to think of a function so that when I take the derivative, I get 2x to the fourth back. Now, the 2 can go along for the ride, okay? And we're going backwards. And so to get an exponent of 4, when I take the derivative, I have to start with an x to the fifth. But the question is, what do I multiply that by? And the way I think about this is I notice that the derivative of x to the fifth is equal to 5x to the fourth. But I don't want that 5. And so to compensate for that, I'm going to divide by 5. And so I'm going to take 2 and I'm going to multiply by 1/5. And so and then of course I have to add c. And so therefore, capital F of x is equal to 2/5 x to the fifth plus c. And the reason why is because of the power rule. So notice if I go backwards. So if I have 2/5 x to the fifth plus c, I need to get 2x to the fourth back. But watch what happens. By dividing by 5, I make sure that that 5 cancels out the 1/5. And so I get 2/5 times 5/1 x to the fourth plus 0, but the 5's cancel, and you get 2x to the fourth. And that's the original function. Now, I want you to watch where I carry this to. So, suppose I start with example 6. Now, suppose f of x is equal to x to the n, where I don't want n to be -1, by the way. And to get capital F of x, you're going to get 1 over n plus 1 x to the n plus 1 plus c. That's how you take the antiderivative of a function where f of x equals x to the n. But I want you to watch what happens. If I take the derivative of 1 over n plus 1 x to the n plus 1 plus some constant c, I'm going to apply the power rule. So I get 1 over n plus 1 times n plus 1 x to the n plus 0. But the n plus 1's cancel, and you get x to the n. So that's the idea there. And I want to look at these examples now. So let's take a look at example 7. And suppose I had f of x equals x squared minus 3x plus 2. So I want to go back here. So notice when we have x to a power, I added 1 to the exponent to get x to the n plus 1. And then I took the n plus 1 and took its reciprocal and multiplied x to the n plus 1 by 1 over n plus 1. I hope that made sense. So that n plus 1 becomes the denominator, and the numerator is 1, basically, when you want to find the antiderivative. Now, so if I want capital F of x, so I'm going to add 1 to the exponent, and you're going to get x to the third. And then I'm going to take x to the third, and I'm going to multiply by 1 over 3. And then I'm going to go minus. That 3 goes along for the ride. The exponent here is a 1. Okay? So I'm going to add 1 to that exponent to get x to the second, but I'm just going to multiply by a half. And then can you think of a function whose derivative is 2? Well, remember that the derivative of x is 1, right? So the answer here is 2x. And then you just can't forget to add your constant of integration. Why? Because you're looking for the most general antiderivative. And so therefore, capital F of x is 1/3 x to the third minus 3/2 x squared plus 2x plus c. That's how you do that one. Example 8. Suppose g of x is 6x to the 5th minus 8x to the 4th minus 9x squared. And so I want capital G of x. And so think of a function whose derivative is 6x to the 5th. And so if you want to use that rule on the page before, remember you're going to add 1 to the exponent. The 6 goes along for the right. So it's 6 times 1 over 6 x to the 6 minus 8 times, add 1 to the exponent to get x to the 5th. And then you're going to multiply x to the 5th by 1 over 5. Remember, 8 just stays there. And then I'm going to go minus 9 times, add 1 to the exponent, I get x to the 3rd. And you just want to multiply x to the 3rd by 1 over 3. And then you're going to add c, because it's a general antiderivative. And so therefore, g of x is x to the 6 minus 8 over 5 x to the 5th minus 3x cubed plus c. That's how you do example 8. Let's keep going. Let's try example 9. Suppose I had h of x is 3x to the 0.8 plus x to the negative 2.5. So capital H of x, I'm going to add 1 to the exponent, and that's going to produce x to the 1.8, but then I want to multiply by 1 over 1.8. So let me write that a little clearer. So I'm going to multiply by 1 over 1.8, and then times x to the 1.8. I added 1 to 0.8. That's where I'm getting the 1.8 from. Okay. And then I'm going to add x. Now, if I add 1 to negative 2.5, I get negative 1.5. And then I'm going to multiply by negative 1 over 1.5. And then I'm going to add c. So this is 3 over 1.8 x to the 1.8 minus, now, minus 1 over 1.5, let me just write that down, x to the negative 1.5 plus c. I'm going to multiply numerator and denominator by 10, so that's 30 over 18, x to the 1.8 minus 10 over 15, x to the negative 1.5 plus c. And then if I just reduce those fractions, I get 5 over 3, x to the 1.8 minus 2 over 3, x to the negative 1.5 plus c. And this is where it's important to talk to your instructor, about the negative exponent, to my way of thinking, we started off with a negative exponent, so it may not be that unreasonable to end on a negative exponent, but they might want you to get common denominator. You want to just find out how far your instructor wants you to simplify this particular one. Okay? Example 10. Suppose I give you this one. Suppose g of t is 7e to the t minus e cubed. This one has the potential to be tricky if you're not careful. E cubed is a number, right? Think of a function whose derivative is e cubed. All right? And remember that the derivative of t is 1. Okay? So if I want the antiderivative, a function whose derivative is e to the t is e to the t. So I'm going to write 7e to the t minus e cubed t plus c. E cubed just goes along for the ride. And I'll leave it to you guys to check that if I take that derivative, I will get the original function. That's exactly what you want. Let's do this one. Suppose I had h of x is secant squared x plus pi cosine x. So capital H of x, if I want the antiderivative, think of a function whose derivative is secant squared x. And you're going to find that that's tangent x. Okay? And then the pi goes along for the ride, and can we think of a function whose derivative ends up being cosine x? And that's going to be sine x plus c. Example 12. Suppose g of v is 2 cosine v minus 3 over the square root of 1 minus v squared. Okay? Now, can we think of a function? Here, I'm going to write it this way first so we can kind of think about this. So g of v, I'm going to rewrite this way. 2 times cosine v. I want the 2 to go along for the ride. And then I'm going to subtract 3 times 1 over the square root of 1 minus v squared. Now, the question is, can you think of a function whose derivative is cosine of v? So in other words, the derivative of what produces cosine of v? And in that brackets, I'm going to put a sign. And so I'm going to get 2 times sine of v. And then I'm going to subtract 3 times. And I'm going to ask myself the derivative of what produces 1 over square root of 1 minus v squared. And that's going to be arc sine of v, or the inverse sine of v. And then I just have to add that constant of integration. Remember, c is constant. And you will find that if I take the derivative of capital G, I will get what I originally started with. Example 13. This one's really good. If I have f of x equals 2x squared plus 5 divided by x squared plus 1. This one's really good and perhaps a little on the tricky side. We don't have any elementary antiderivatives the way it's written. Let me say it another way. I don't know the antiderivative of this until I split off this, until I do the long division, I should say. So this is what I'm going to do. I'm going to take f of x, and I'm going to write this as 2x squared. I'm going to break the 5 up into 2 plus 3. So plus 2 plus 3 divided by x squared plus 1. And this takes time, but watch what happens. I'm going to take 2x squared plus 2 divided by x squared plus 1 plus 3 over x squared plus 1. Okay? Now, factor a 2 out of the numerator for the first term. And then I'm going to write this as 3 times 1 over x squared plus 1. But if you notice, the x squared plus 1's cancel. Okay? Therefore, f of x is 2 plus 3 times 1 over x squared plus 1. Now, that's how we essentially, I split off that fraction. Okay? Now I want capital F of x. And so a function whose derivative is 2 is 2x. The 3 goes along for the ride. Okay, that's why I multiply by 3, because I want you to focus on this piece. Think of a function whose derivative is 1 over x squared plus 1. And you're going to find that that's the arctangent of x. And then I just have to add c. And that's how you do that example. That was example 13. So let's do a couple more. Example 14. Suppose I give you something like this. F of x is 2 over 5x minus 3 over x squared. Something like that. Okay, I'm going to recommend you write it this way. So I get 2 over 5 times 1 over x. Okay, and then I'm going to go minus 3 times 1 over x squared. And so this is 2 over 5 times 1 over x minus 3 times x to the negative 2. Now, think of a function whose derivative is 1 over x. Remember that 2/5 goes along for the ride. And so capital F of x, we have to label it as our antiderivative. Okay? And so this is 2/5 times the natural log of the absolute value of x minus 3 times x to the negative 1 divided by negative 1. Here, I'm going to do it a little better, actually. So the way we've done it is, remember that you're adding 1 to that exponent. So we're making it x to the negative 1. Remember that negative 2 plus 1 is negative 1. And then we multiply by 1 over negative 1. And then I'm going to add c. And so this is 2/5 natural log of the absolute value of x plus 3 over x. Remember that x to the negative 1 is 1 over x. And 3 times 1 over x is 3 over x. And then I just add c. And this whole thing is equal to capital F of x. Example 15. let's make this the last one for this video. If I give you f of x is 10 over x to the 6th minus 2e to the x plus 3, I'm going to write this as 10 times x to the negative 6 so I could look at it straight, minus 2 times e to the x plus 3. And if I go to take the antiderivative, I'm going to take 10 times, I want to add 1 to that exponent to make it x to the negative 5. But remember, I have to divide by negative 5, so, or multiply by 1 over negative 5. Those mean the same thing, by the way. So dividing by negative 5, multiplying by 1 over negative 5, same idea. Think of a function whose derivative is e to the x. Well, that's just e to the x. So I'm going to take e to the x, multiply by 2. Think of a function whose derivative is 3. That's 3x. Then I'm going to add c. So this is negative 2 over x to the 5th minus 2e to the x plus 3x plus c. And this whole thing is equal to capital F of x. And this is a good stopping point. This will conclude this video for section 4.9 on antiderivatives. And we did 15 examples. So in the next video, I'm going to do further examples where we also have what are called initial conditions. Okay, thank you.